Welcome and thank you for joining. Let's take a look at another question with three intersecting planes. So as you can see, we are given the equations of three planes in scalar form, and we're going to start off by numbering them as equations 1, 2, and 3. Now, to find the common points of intersection means to solve this system of equations. And whenever we solve these systems of equations, we start off with step number 1, comparing the normals to each plane. The reason why we want to compare the normals to each plane is because we want to see how the planes are positioned against each other, because that can give us an idea of the type of intersection that can occur between the three planes given. So you know that three planes can intersect at a single point, can intersect along a common line, or they can have a common plane. So if you look at the first equation, 2x plus y plus z equals 1, the normal is determined by the coefficients of x, y, and z respectively. So we'll say that the normal will have the coordinates 2, 1, 1. For the second equation, the normal would be 4, negative 1, negative 1. And when you look at the last equation, notice how the coordinates here, or the coefficients, are all even numbers, which tells us that they can be reduced by 2. It is best to reduce each equation to lowest coefficients possible, because that would make the understanding or the connection with the other normals a little bit more clear. So we are dividing every term in the equation, both sides of the equation, by 2, and that will create the more simplified form of it, 4x minus y minus z equals 5, which tells us that the normal to the plane pi 3 would be 4, negative 1, negative 1. So when you compare the normals now, notice how the normals of planes 2 and 3 are exactly the same. And not only this, but their constants are the same. So the value of d, which is when this number is taken to the left side of the equation, is negative 5. And the value of d here is also negative 5. So the d values are the same, which makes these two planes not only parallel, because their normals are the same, but also it makes them have a common point, which tells us that these two planes are coincident. So now let's try to picture the whole situation together. So it seems that we have two planes that are coincident. Here are the planes pi 2 and pi 3. And plane pi 1 is cutting through, and the common line of intersection will be this line in here. So this is the line whose equation we're trying to find. So let's get to work. We've arrived to the second step. And in step 2, guess what? We are going to try to create two systems of two equations. Now recall that when we create the two systems of equations, it doesn't really matter how we pair them up. So we can pair up 1 with 2 and 2 with 3, or 1 with 2 and 1 with 3, doesn't matter. And the way that I chose to pair them up this time were 1 with 2 and 2 with 3. So once we create the two systems of equations, move on to step 3, we eliminate one of the variables. Now remember that whatever variable you eliminate from the system, from the first system, you got to eliminate from the second system. So if you eliminate z from here as well. If you eliminate y, then you have to eliminate y, and so on. You get the idea. So in this case, what I'm going to try to do is eliminate the variable y. So I would be able to do this by simply adding the two equations together, because the y terms have opposite coefficients. So same value, opposite signs. So that will give us 2x plus 4x, 6x. 1y plus negative y is 0y. Z plus negative z is 0z, equals 5 plus 1 equals 6. Now 0 multiplied by anything is 0, so it seems that here we have 6x equal to 6, which gives us actually a real value for x, so x equals 1. So it seems that we have found the x value on the common line of intersection, and that would be equal to 1. Now, let's take a look at the second system of equation. Now, we're going to eliminate the variable y again. And as you can see here, we need to modify the equation a little bit, because the y term in the first equation has a coefficient negative 1. Here we have negative 2. So I will be multiplying here by 2 every term in the first equation. I mean, that's equation 2, but first equation in that system. And that will give us 8x minus 2y minus 2z equals 10. That would be our equation 2. And equation 3 is 8x minus 2y minus 2z equals 10. Oh, wait a second. So it seems that we obtained the same equation in here. So we are, if we were to subtract these two from one another, then we will get 0x, 0y, 0z equals 0. So this is true for any real value of x, y, and z. So we're going to say that any value of x or y or z can satisfy this equation. And when you think about it, this makes sense because we know that there will be an infinite number of values or infinite number of solutions or ordered pairs x, y, and z that can satisfy the equation, which means that we will get infinite number of common points. And we know that we are obtaining a line as a common intersection here, and on a line we have an infinite number of points. So we're not surprised by it. But then what do we do next? So remember that once we find the value of x equals 1, then x equals 1 should satisfy equations 1, 2, and equation 3. But recall that since equations 2 and 3 ended up being the same thing, it means that our job is a lot more simplified now. All we have to do is substitute x in equations 1 and 2 or in equations 1 and 3 because 2 and 3 are the same thing. So, step number 4. And this is where the steps start diverting. So the first 3 steps are the same. So comparing normals, create 2 systems of equations, eliminate one of the variables. So this is standard practice. So if you have a question like this on an evaluation or a test or exam or whatsoever, so even if you have no idea how to proceed and you cannot compare the planes, then what you have to do is simply follow the steps of find their normals, create the systems of equations, eliminate one of the variables, and then you will figure out the rest with a little bit of faith and persistence. So step number 4 is substituting x by 1. And this is a unique situation in this case because we obtained an actual value for x. So the first equation, which is 2x plus y plus z equals 1 with x value of 1, will create y plus z equals 1. So that will make y plus z equal to negative 1. Now, if you try to substitute actually x by 1 in the second equation, say, for example, for x minus y minus z equals 5, then interestingly, you will notice that we obtain in this case the exact same equation as before. And this is thanks to the fact that planes pi 2 and pi 3 are the same. Now, I wanted to go over this so that we can see the connection between what the algebraic solutions would look like, or what our findings will be when we solve the system of 3 planes algebraically, right? And how the normals can tell us what kind of intersection will exist between the planes, so how the planes are positioned against each other. So what we have in our hand right now is the following information. So first of all, we know for sure that x would be equal to 1. And for the other coordinates, y and z, all we know is that when added together, that will give negative 1. Now remember that x equals 1 and y plus z equals negative 1, so these coordinates are all going to be on the line of intersection because we found these relationships by combining all 3 equations together. So when you think about the variables y and z, there is no possible way to list all the possible values of y and z because there is an infinite number of ordered pairs y and z that can satisfy this particular equation. So if we were on the Cartesian plane, for example, where we drew let's say, a specific line, y equals, I'm going to say this is y equals x plus 2, for example. So if we want to actually list all the possible points, it's impossible. So we're going to say, oh, this is where all the points are. And whatever x is, y would be equal to 2 more than x. So since we cannot find specific values of z and y, because there are so many of them, right? So what we are going to try to do is describe those values instead. So the standard procedure or process that we follow is we let one of these variables be a number, any number. So we're going to say let y be some number. And for this, we're going to use a letter of the alphabet. So for example, we can use letter T, letter S, letter W, V. It doesn't really matter. So very commonly, actually, it's letter lambda is commonly used in these type of questions as well. So you may encounter it in some older fashioned textbooks as well. Anyways, so back to our solution here. So we're going to let y be any real number t. So, and I'm going to make a note in here where t is a real number. So whatever the value of y is, then the z value will be negative 1 minus y. So that will make the value of z equal to negative 1 minus t. So therefore, we're going to say that, yes, we cannot list all the possible values of x, y, and z in here, but we know that x would be 1, and the y value will be t, and the z value would be negative 1, take away the value of t. So as you can see here, like in this particular equation, y equals x plus 2, yes, we cannot list all the possible points. We can find specific points if the need arises. But if we want to find out where are the points on this line, we're going to say, well, the points are wherever y equals x plus 2. So in a similar way, if we want to describe all the points that lie on this line, we're going to say, well, we don't know all of them. We can find specific points if you wish, but all we know is x will be 1, y will be some number t, and z will be negative 1 minus that number t. So we find what we call the parameters x, y, and z in terms of some other number, any number, right? T, which is any real number t. So if you look closely at these three equations, which I'm going to box them up actually, so they get our full attention. Now, these are practically parametric equations of a line. I'm going to make some room so we have them close enough to each other. So we're going to say that if we were to involve t in every parametric equation or in the equation that describes every parameter, x, y, and z, then x will be equal to 1 plus no t, 0t. The value of y would be equal to, you don't see any constants in here, so we're going to say 0 plus 1t. And the value of z will be negative 1 minus 1t. So purposely, I wrote the coefficient negative 1 here because we're about to write the equation of this line from parametric to vector form. So we're going to say any point with coordinates x, y, and z on this line will be equal to the position vector, which is 1, 0, and negative 1. So 1, 0, negative 1. So that's the position vector. And then plus the coefficient t. Let me make this perfect. So plus coefficient t. And then the coefficients of t in each parametric equation we know will be the coordinates of the direction vector of the line. So 0, 1, and negative 1. So therefore, we're going to say that the common line of intersection will be at 1, 0, negative 1 plus t, 0, 1, negative 1. Now, when you look at this direction vector, notice that x is equal to 0 and y and z have values different than 0. So I want you to think for a moment, where in R3 is this direction vector located? So when you look at it, since x would be equal to 0, remember z, x, and y axis. So x will be equal to 0 when the direction vector here, or x will be equal to 0 when a point is on the z, y plane. So the direction vector will be somewhere here. And that's why x was a fixed number here in the solution. So we're going to say that the direction vector would be on the zy plane or yz plane, however you want to say it. So it's nicer to say them in alphabetical order. But I see zy very often as well, so yz plane. Okay, so if you want to see the solution to this system a little bit better, you can always graph it on GeoGebra, the good old GeoGebra. So let's get back to this. So I tried to prepare it, but let me see if the equations are here. Yes, so 2x plus y plus z equals 1. That's the first equation. And in the meantime, I'm going to actually change the colors of each plane, actually. So let's make this color a little bit more pronounced so we can see it better. So I'll make it darker blue. And then the second plane, I will change the color of it. Let's make it red. And for the last equation, we're going to change the color as well. And we're going to make it green, darker green, so that we can see it better. Okay, so let's take a look at where the planes intersect. So notice how we have the red and the green plane, right, overlap, so they will make the same plane. And it is the, you see, so the red and the green have made this kind of orangey plane if you look at it, okay? And you also notice that the purple plane, so the first one, is intersecting along this line right here. And as you can see on this line, the x values will be following the direction vector, which is on the zy plane and yz plane, and the values of x would be equal to 1. So I was just thinking, maybe give me 1 second. I'm just going to take a snapshot of this so that we can take a better look at it on the, I don't want to lose the axis. So, okay. So I think we have a good enough view here. So let me just bring it on the screen so we can see it a little better. By the way, try to use the GeoGebra tool as often as possible and try to get used to it as well, as much as you can. And that is because it is very helpful tool actually in university as well. So it is very helpful. And the more familiar you are with it, and the more and the better, more efficiently you can use it to understand the solutions. So I'm going to have to open up a new page here so that we can have a better view. Okay, so when you look at the intersections made in here, you see the planes pi 2 and pi 3 will overlap. So you see where they are. Okay, so and they have turned into this weird color. Remember that we had two different colors, like I think orange and green, so they made this brown color because they are merged together. And this, the purple one here would be the plane pi 1. And the common line of intersection, I'm going to make it red just like we had it before, will be right here. Oops, not very good. Okay, I'm going to try to bring it closer. I don't think that I can though. Yes, that's what I thought. Let me just do this a little bit differently. So I'm going to draw a line starting from the outside of the graph. So this is the common line of intersection. Okay, so I have to, okay, now I can do this. Okay, this is a common line of intersection. So as you can see, the common line of intersection here will have the x value of 1 right here, if you notice, okay? And the direction vector will follow the YZ plane. So this is the YZ plane, okay? So, and the x value would be always equal to 1, following the direction. And that's the reason why we got x equal to 1 right away here. So I hope this made sense, and continue learning with enthusiasm and persistence always. Bye for now.